In this video, we'll take a look at the final step that converts the vector produced by the decoder into an actual word choice, namely the linear layer and the softmax layer. In the final part of the transformer architecture shown here, you can see how the output vector, generated by the decoder, is converted into probabilities through the linear layer and the softmax layer. The linear and softmax layers together form the step that transforms the decoder's vector into an actual word choice. First, the output vector is projected into the vocabulary space by the linear layer, where a score, called a logit, is computed for each word in the vocabulary. Then, the softmax function is applied to these logits to convert them into a probability distribution. And based on this distribution, the next word is ultimately selected. As an example, let's use the sentence, "I like baseball better," as the input. This sentence first goes through the tokenization process, where it is split into individual tokens. Then, through embedding and positional encoding, it is converted into a vector representation with a dimensionality of 4 by 512 and fed into the encoder. Based on the information passed from the encoder and the previously generated tokens, the decoder produces one output vector for each token, but the last token vector is used to predict the next word. At this stage, the decoder output can be represented as a 4 by 512 matrix, which we denote as H. Each vector in H contains the contextual information up to that token position, and for next word prediction, only the output vector at the final token position is used. In other words, the last token vector, H better, is used to predict the next word following "I like baseball better." Now let's take a look at the role of the linear layer. As this final output vector passes through the linear layer, it is projected into the vocabulary space, where a score for each word in the vocabulary is computed. These scores, called logits, represent how likely each word is to appear next. As shown in this example, the vector H better represents the output vector of the last token from the decoder. A linear transformation is applied to this vector to compute the next word candidate scores or logits for each word. Here, W vocabulary denotes the weight matrix that projects the decoder output vector into the vocabulary space, and B represents the bias term associated with each word. In this slide, we examine how the linear layer actually computes logits through an example. First, W vocabulary is a weight matrix that projects the output vector from the decoder into the vocabulary space. An interesting point is that the weight matrix that projects the decoder output into the vocabulary space is shared with the input embedding matrix using its transpose. That is, at the output stage, the transpose of the embedding matrix is used. Here, H better represents the output vector of the last token, generated by the decoder for the sentence, "I like baseball better." This vector is dotted one by one with the embedding vectors of each word included in the vocabulary. And for each word, such as than, more, very, and good, a score indicating how well it matches as the next word, that is, a logit, is computed. Through the equation explained in the previous slide, a logit vector for all words in the vocabulary is produced, and the dimensions of the vectors and matrices at this stage are shown below. These computed logit values represent the relative magnitude of the likelihood that each word will appear as the next word, and they are then converted into a probability distribution through the softmax function. Now let us take a look at the softmax function. Softmax is a function that is widely used in multi-class classification problems, and it plays the role of converting the given input values, that is, logits, into a probability distribution over classes. It is mainly applied at the output layer of a neural network, where all output values are expressed as probabilities between 0 and 1, and the sum of all probabilities becomes 1. The softmax function is defined by the following equation. Here, z represents the logit for each word included in the vocabulary, by applying the exponential function to each logit value, and then normalizing by the sum of the exponential values over all logits. A probability distribution is computed. In the output stage of the transformer decoder, the logits computed by the linear layer are fed into the softmax function and are used to compute a probability distribution over all words in the vocabulary, representing the likelihood of each word appearing as the next word, based on the output vector generated by the decoder. Now, after computing the logits for all words in the vocabulary, we will look at a simple example of the process in which these logits are converted into a probability distribution through the softmax function, and the next word is selected based on those probabilities. For the purpose of explanation, we will use only 4 words as examples: than, more, very, and good. As the final output vector of the decoder, h better, passes through the linear layer, logit values are computed for each of these 4 words. When the softmax function is applied, a probability distribution over the next word is obtained as shown below. As you can see in the table, than has the highest probability of 0.58, so the model selects them as the next word. As a result, the sentence is extended to, "I like baseball better than." This result then becomes the input sentence for the next prediction. In other words, the sentence, "I like baseball better than," is tokenized and embedded, resulting in an input of dimensionality 5 by 512, and the same encoder-decoder process is repeated to predict the next word. By repeating this process, the transformer generates a sentence sequentially, one word at a time.